So here, this is a discussion about PN junction diode. Actually, why we learn about the intrinsic semiconductors and extrinsic semiconductors? Because we have N-type semiconductor material and P-type semiconductor material. By using these two types of semiconductor material, if we form a junction, and that particular junction can show a lot of behavior in the electronics engineering field, or this particular junctions made by P-type semiconductor material and N-type semiconductor material behaves certain peculiar property, or which exhibits certain peculiar property that actually makes to devise certain kinds of devices in electronics actually, or that particular junctions formed by P and N-type materials, semiconductor materials, that actually makes a PN junction, and that particular junction is very widely known as a PN junction diode. So what are all diodes, what are all transistors, and how this behavior is used in the operation of transistors and diodes? That is the main discussion we have to have in the coming sessions. And here I will just give you an understanding about the PN junction diode. Okay. Now, how a PN junction is formed? When a P-type semiconductor material is joined with an N-type semiconductor material, a PN junction is formed. Just like this one. This is a P-type silicon material, and this is another N-type silicon material. And here, this particular junction is made by silicon, P-type and N-type material that are joined together, and the end will be having some metallic contacts like this. So that the P-type material, the terminal connections to P layer is usually called an anode, and the terminal connections to the N layer is called cathode. Or the P-type material, the terminal is connected to this particular metal piece, and that will be acting as the anode. And in the N-type material, this metal piece or conducting material will be acting as the cathode, isn't it? So here, this particular junction is what is called the PN junction. This particular junction is called a PN junction. Here, the junction is formed by the P-type material and N-type material. That is why it's called the PN junction. And this PN junction is usually represented in an electrical symbolic way. And this PN junction is actually nothing but a PN junction diode. So such PN junction diodes are symbolically represented with the help of a diagram like this. So this is a symbolic representation of or electrical symbol of a PN junction diode, and this will be representing the anode. The arrow direction will be representing the flow of current, and this is the cathode. This is the cathode. Okay. What are the important characteristics of a diode? So, do you know what are the important characteristics? You might have learned it in the high school classes. The PN junction diode can conduct current only in one direction. Or this junction, this particular device, this junction device, what is called the PN junction diode, can exhibit a particular behavior. What is that particular behavior? You know, when this particular material junctions are subject to a source of EMF, then depending upon the connections given to this particular PN junction device, the device may either conduct the current or which may not conduct the current. Understand? So it means that depending upon the connections given to this particular PN junction diode to an external source of EMF, the diode can conduct current in one direction, or which will not conduct current in the opposite direction. That is the basic characteristic of a PN junction diode, which is able to conduct current only in one direction, or it is a device called a unidirectional device. A unidirectional device means a device which can conduct current only in one direction. That is unidirectional device. P region has holes, negative and negatively charged acceptor impurity ions. N region has electrons, and we have seen N region has a large abundance of electrons available and positively charged donor impurity ions. The P region has large number of holes available and negatively charged acceptor impurity ions available. And the holes and electrons are mobile charge barriers. in the case of this particular device. Holes and electrons are mobile charging. What is meant by why it's called mobile charge carriers? Because the mobility of the charge carriers are due to the electrons and holes, and ions are immobile. What is called ions are immobile? Due to the recombination of electron-hole pairs in the valence band, I told you there will be negatively charged ions possible in the case of p-type material, and there will be positively charged ions in the n-type material. So the n-type material, the positively charged ions generated are immobile in nature. Only electrons are moving depending upon the, or electrons are mobile in nature. Mobile means moving in nature. So moving in nature. So that actually constitutes the current flow. So thermally generated electrons and holes are also present at P and N region. Thermally generated means due to the surrounding temperature, whether it is increased or decreased, electrons and holes are being present at the P region and N region. So let us see here the P-type material, N-type material. So which forms a P-N junction here. This is a diagrammatic representation. So at P-type material, of course, there will be holes available. N-type material, there will be large number of free electrons available. When these P-N junctions are formed, there will be large number of positively charged ions available on the N-type material with a large number of free electrons. There will be large number of negatively charged ions available, that is the acceptor ion available on the P-type material. That is diagrammatically shown here. And donor ion, that is positively charged in the case of here, and acceptor ion in the case of negatively charged acceptor ion here in the case of P-type material. And here, this gives rise to a large number of free electrons shown here, and this gives rise to a large number of holes here. Okay. Then when a P junction diode is with no external voltage applied, or when there is no source of EMF applied, or when there is no applied voltage to a PN junction, what happens to a PN junction? So when there is no voltage applied means the PN junction is in its normal usual condition. As soon as the PN junction is formed, what happens? The holes from the P side diffuse from P side to N side, where they combine with the free electrons available. And the free electrons in the N side there will be a large number of free electrons that will be diffused to the P side and recombine with the number of holes available there. It will be recombined with this hole. So near the junction, combining of these electrons and holes resulting in a region which contain only immobile ions. When electrons are recombining with the holes in the P side, there will be what happens? There will be negatively charged ions there. That is immobile in nature. When the electrons are, when the holes are recombining with the electrons in the negatively charged, more negatively charged, that is N-type material, what happens? There will be a recombination of electron hole pairs creating a positively charged ion. So that is immobile in nature. So this immobile electron hole pair combinations actually diffuse into either side, creating a region. Usually that region is called the depletion region or space charge region. Do you know what is the space charge region? When PN junction is formed, we didn't give any external voltage or we didn't give any electrical field to the system. We didn't give anything. When a PN junction is formed, that means when a P material is made joined with an N-type material in order to form a PN junction in between. As soon as the PN junction is formed, what happens? The number of holes available on the P side, that will be diffusing to the N side, N-type material side, forming electron hole pair combination. Similarly, N-type material is having large number of free electrons that will be combining with the holes in the P-type material, forming electron hole pair combination, so that it becomes an immobile ions with the recombination of electron hole pairs. So these immobile ions formed in the region is usually called a depletion region or a space charge region, where the electron hole pairs have been recombined and which forms a region which is called the space charge region. And what is the behavior of this region? See, here it is shown here. So negative charge ion will be recombined with the positive charge holes, and positively charged that is n-type material. So here this will be this p-type material having holes will be recombining with electrons in this one and creating positively charged ions here, negatively charged ions in the p-type material. So this particular region where this recombination takes place is called the depletion region or space charge region. And this region in effect will be acting as an electric field. That is because this region is actually formed by the recombination of electron hole pairs, isn't it? And in effect, in the junction, in the PN junction, this particular region will be acting as an electric field. Follow my point. And this particular electric field will be appeared as a voltage. Usually that will be appeared as a voltage because this region has no charge carriers because it is a depleted region. It's a depleted region. Why is it depleted? Because in this region, in the PN junction, in the region of the PN junction, the n-type material, n-type that is electrons and holes from the p-type and the electrons from the n-type has been recombined together in order to form the positive or negatively charged ions, which are immobile in nature. So in effect, there is no charge carriers there, or that particular region, which is usually depleted due to the recombination of electron hole pairs on either side. See here, this electron hole pairs actually makes this particular region depleted with the charge. There is no excess charge available here. There is only combination of this electron hole pairs that converts into as a charged, that is ions, charged ions. So which is immobile in nature. So in effect, there will be a space charge region which will be acting as a region with an electric field in between. And this region is having no free electrons or free holes. There is no free electrons or free holes. There is no free charges available. So there is no mobile charges available here, whether electrons or holes. This is a space charge region which are depleted with charge carriers, but this space charge region which will be appearing as an electric field with a small voltage depending upon the type of material. Okay. And that particular region, this region has depleted. There is no charge carrier. And that is why it is called space charge region, because this region contains charged ions only, because there will be only the space charges that recombines with each other in order to maintain a charged ion. A charged ion means immobile ion, charged immobile ion. This region creates a potential difference across the junction called barrier potential or space charge potential BB. That is shown here. Actually, there is no connections done like this, but this is a symbolic representation of the space charge that will be appeared as an electric field with a voltage VB that will be always opposite to the applied field. See here, this is the applied field with the positive voltage applied here when this switch is closed. When the switch is closed, this is the positive polar P-type is connected here like this, and then N-type is connected onto the negative side of the source of EMF. And this space charge region that will be acting as a space charge, that is charge having an electric field with positive and negative polarity, and that will be appeared as an electric field like this with a voltage VB. And this voltage will be, or this space charge voltage will be always opposite to the applied EMF E. If this applied EMF is E, then VB will be opposed to the applied voltage E. So E has to drive through a current he has to send a current through this one by driving to make up this voltage. Then only the current flow will be constant. So this opposing voltage has to be overcome by the applied voltage. That's what I said. This region creates a potential difference across the junction called the barrier potential or space charge potential, because this is a region having space charges with a polarity, so that this potential is called the space charge potential, which is appeared as a barrier. What is meant by barrier? Barrier means obstacles. So which is appeared as an obstacle for the current flow. So in other words, this space charge potential created here due to the joining of the PN junction will be or will have to be overcome with the applied voltage E here. If this applied voltage is E, then E has to work upon this particular junction against this voltage VB in order to send a current. That is why this voltage is called a barrier potential or potential which is arised at the space charge region. That is what is called the space charge potential. Either you can call it as a barrier potential VB or a space charge potential VB. Understand? VB means V voltage barrier. So these images only barrier potential. And this VB, the space charge potential may be, the space charge potential will be 0.3 volt for germanium type PN junction, and that will be equal to 0.7 volt for silicon type material. So for silicon type material, P type and type materials are joined together. If this material is a silicon material, or if it is a germanium material, if it is a germanium material, the space charge potential arised by joining the PN junction is 0.3 volt. Or if you are connecting an external voltage, and if the switch is closed, this external voltage E can send a current through this one by opposing this space charge potential, by overcoming this barrier potential or space charge potential. Understand? So this VB will be numerically equal to 0.3 volts in the case of a germanium material. If PN junction diode is made of germanium material, then the space charge voltage appeared will be 0.3 volt. If it is a silicon material, the space charge voltage will be about 0.7 volts at room temperature. That is at 30 degrees centigrade or so. This potential prevents further diffusion of charge gases. So initially, this potential which created due to space charge, that ultimately caused to prevent the further diffusion of electron hole pairs here. So at the region, at the PN junction region only, this space charge potential appears. And that actually helps or prevents further diffusion of electron hole pairs like this. Understand? So that actually makes the electron hole pairs diffusion further, that is prevented. Understand? Hence, without external bias or without giving an external voltage here, or if the switch is opened, there is no voltage applied here, there will be only the barrier potential which is created at the space charge region of the PN junction. Understand? So without external bias, there won't be any current flow through this diode. There will be only a space charge potential which appears across the PN junction diode. There is no current flow through the PN junction. So when there is no external source of EMF applied, there won't be any current flow through the PN junction. Now, if this particular PN junction, this is the PN junction, is not shown here, P and this is P and this N, here this particular area, the PN junction is formed, isn't it? So if you apply the positive polarity point connected to the P type side and negative polarity point of the external source of EMF applied to the N type or N lead of the diode or PN junction diode, then what happens? The positive polarity point is connected to the P side and negative polarity point of the source of EMF is connected to the N type lead of the PN junction. Then what happens? then at that particular situation or that particular condition, kind of operation of the diode is called the forward bias condition. Or if this particular diode is forward biased, when the p-type material is connected to the positive polarity of the battery or source of EMF, and n-type polarity is connected to the n side, that is negative side of the source of EMF. Okay, that particular connection is called the forward biased connection or forward biasing of the PN junction. Or under this particular condition of connection, the PN junction is forward biased. So in forward biasing, positive terminal of the voltage source is connected to the P region and negative terminal of the source is connected to the N region of the PN junction. Holes are repelled by the positive terminal and moves towards the junction. Electrons are repelled by the negative terminal and moves towards the junction. That is shown here. Holes are repelled, isn't it? Because this, holes are repelled and electrons are moved towards the junction. And here the electrons are repelled, and because here there are number of electrons that are repelled and which are moved to the towards the junction, isn't it? Which are moved towards the junction because the electrons are repelled by the negative polarity and hence it is reached towards the PN junction. Because of acquired energy from the voltage source, some of the electrons and holes penetrate the depletion region and recombines themselves. Because of the acquired energy, because when a potential source is connected to the PN junction diode or PN junction device, what happens? Of course, it will be acquiring some energy, isn't it? Though the space charge region is there, some of the electrons and some of the holes in the either side of the PN type material, which acquires energy, some of the electrons and some of the holes which acquires energy and penetrate through the depletion region, which penetrates through the depletion region and recombine themselves. Okay, so that is shown here. So that is why what happens when it recombines. Initially, when there is no voltage connected, this is the depletion region. But when the voltage is connected, when the voltage source VF is connected or EF is connected here, what happens here? This electron hole recombination takes place. Effectively, what happens, this depletion region gets reduced. The width of the depletion region gets reduced. When no voltage is applied, the depletion region has a wide depletion region. The width of the depletion region is very wide. But when the voltage is applied, some of the electrons gain energy on the, some of the holes gain more energy and crosses this junction and reaches at the and recombines with the electrons in the n-type material, and some of the electrons here also recombine with the holes here, so that an electron hole recombination takes place, and that actually makes the depletion region reduced. Okay, so that is why here the depletion region is very large. Now voltage is applied. Here the depletion region is getting reduced when positive polarity is connected to p-type and negative polarity is connected to n-type material. Then this reduces the depletion region as well as the barrier potential. So when the depletion region is getting reduced, what does it mean? The barrier potential or the space charge potential is getting reduced. As a result, more majority carriers and holes from the p side and electrons from the n side diffuse across the junction, and finally a large current flows through the PN junction when the applied voltage is increased more than the space charge voltage or barrier potential. When the applied voltage is increased in such a manner that if the applied voltage is more than the space charge region voltage, that is the depletion region or barrier potential, then what happens? The current will be increased more and more. So in a forward biased condition, so what is that forward biased condition? Positive polarity is connected to the p-type material and negative polarity is connected to the n-type material, and so that the EMF source will be sending a current through this PN junction when the applied voltage increases just above the depletion region voltage, that is the space charge region voltage, that is what's called the barrier potential. If the applied voltage is just above the barrier potential, this diode will start conducting current from positive to negative through this. right? So it starts conducting current through this direction. So the width of the depletion region is getting reduced, the value of the barrier potential is getting reduced, or junction offers low resistance for the current flow. At this particular condition, when the applied voltage just increases the value of the depletion region or value of the depletion region voltage, that is the barrier potential, then it starts conducting and the junction offers very less resistance for the flow of current. Junction offers a very less resistance for the flow of current. If the voltage is further increased, then the current flow through this junction is also increased in accordance with the increase in voltage here. So finally, what happens, when the voltage is increased above the space charge voltage or the barrier potential, there is effectively no barrier potential available there. The PN junction will be conducting current through the junction, right? Or in other words, junction offers a very least resistance for the flow of current. The magnitude of the current depends upon the applied voltage. That is, if you are just varying the applied voltage in such a manner that if the applied voltage is more than the barrier voltage, it starts conducting and high current will be flowing through the system. If the voltage is further increased, so it will be sending more current. Here, the switch has to be closed. Here, the switch is now open. It has to be closed for doing an experiment like this. So, or here it is shown here. So, this is what is called the forward biasing. So, in forward biasing, the diode conducts. The diode conducts in the forward direction. In forward biasing, the diode conducts in the forward direction. And in the reverse biasing, what is the reverse biased condition? In reverse biased condition, what do you know? The terminal voltage of the source is connected to the N region. What terminal? The positive terminal of the voltage source is connected to the N region of the PN junction. And the negative terminal of the source is connected to the P region as shown here. So it is shown here. So here P-type region is connected to the negative terminal. N-type region is connected to the positive terminal. In this condition, we say that this particular PN junction is reverse biased. Because, why is it called reverse biased? Because the holes in the P region are attracted by the negative terminal. The holes in the P region are attracted towards the negative terminal. The electrons in the N region are attracted towards the P terminal of the or positive terminal of the voltage source. The electrons in the N-type N region will be attracted towards this one, and the holes in the P region will be attracted towards the negative polarity of the voltage source. So in effect, what happens here? In effect, what happens? The depletion region will be getting widened further. The depletion region will be getting widened because most of the electrons will be getting attracted towards the most of the holes will be attracting towards the negative polarity of the voltage source, and most of the electrons here will be attracting towards the positive polarity of the voltage. So that actually ultimately causes to make the depletion region widen further. So without having any voltage source applied, this is the width of the region due to the recombination of electron hole pairs. But when the voltage source is reversed or voltage applied to the PN junction is reversed, that is P-type connected to the negative polarity, N-type connected to the positive polarity. That is what is called the reverse bias. And at this particular condition, the depletion region at the PN junction will be getting widened further due to the reason I have just explained now. So this increase in width of the depletion region causes a very high resistance across the junction. So the junction resistance will be very, very high of the order of so many megohms sometimes. So in other words, there won't be any current flow through this PN junction when it is reverse biased. A PN junction, when it is reverse biased, will not conduct current through the PN junction. That is the idea. Okay. This increased barrier potential prevents the diffusion of majority carriers and no current flow due to the majority carriers. Understand? So the increased barrier potential prevents the diffusion of majority carriers. There is no majority carriers possible there because the depletion region has been widened due to the application of a reverse potential. So that is why there is no current flow through the junction, PN junction. No current flow is there due to any magnetic carriers there, because the depletion region has now widened due to the application of the reverse potential across the PN junction. But the barrier potential helps minority carriers to cross the junction. This barrier potential, which is now very much widened due to the application of a reverse potential, that actually causes to cross a very, very few minority carriers. That's why it is called minority carriers. A very few minority carriers. Even if that carriers, minority carriers are very smaller number, very small in number, but it's a minority carrier. And that minority carrier will also constitute a current in this PN junction or across the PN junction. And that minority carriers that constitute a current across the PN junction, and that current is due to the minority carriers, and hence it is called a leakage current, because the device is now reverse biased. There is no effective flow of current through the junction. Only current flow is due to the minority carriers, that is due to the very small electrons generated due to the thermally generated electrons and the barrier potential created. So that particular electrons are called minority carrier electrons, that will be setting a current across the junction called leakage current. Okay, that will be creating a current called leakage current. So this is a reverse biased PN junction. Here this is the applied voltage VR, that is V reverse, and that actually causes to widen the depletion region. Here the depletion region has got a very wide gap, so that if you want to send a current through this one, you have to apply very high voltage across the reverse bias junction. Or ultimately what happens, if you apply very high voltage across the reverse bias junction, there is a particular voltage called peak inverse voltage of any diode or a PN junction device. And that peak inverse voltage is due to the voltage when the diode is reverse biased, or it is that reverse voltage up to which the diode will resist the application of a voltage in the reverse biased condition. If the reverse voltage is more than this PIV, peak inverse voltage, that will ultimately cause to break down this junction, and that breaks or that will damage the PN junction. That will damage the PN junction. So in a reverse biased condition, you have to apply a reverse voltage that should be always less than what? Less than the peak inverse voltage of the diode. So peak inverse voltage of a diode is a very important specification of the diode. Okay, so that I will tell you. Here a very small number of electrons that is generated due to the thermally generated electrons that will be crossing this junction due to the energy possessed by it and reaches here in the form of leakage current. These electrons, though it is minority carrier, produces a current that is what is called the leakage current through the junction during reverse biasing. So during reverse biasing, the current through the junction is only the leakage current. There is no effective flow of current. The only current flow through the junction is the leakage current, that will be of the order of some microamperes. Micro means 10 raised to minus 6. That's a very small current, because under normal condition, the diode may, when it is forward biased, the diode may conduct either milliamperes of current or amperes of current, because it is the forward biased condition or current flow condition. But when the diode is the reverse biased condition, where the voltage applied is in a reverse biasing condition, the diode will not conduct current through the junction. Instead, there will be a very small minority carrier current flow due to the thermally generated and the large that depletion region formed. So this thermally generated electrons will be flowing across, or that will be moving across the junction as a leakage current. So under reverse biased condition, the current flow through the PN junction will be always leakage current. Under reverse biased condition, the current flow through the PN junction will be always the leakage current, that will be of the order of some microampere. For reverse biased condition, PN junction current leakage current, and that is not an ordinary current flow. It is a leakage current flow due to the thermally generated electrons, and that current will be of the order of microampere, such a small value. But in the forward biased condition, what happens? Effectively, the depletion region get diluted or it gets reduced. So finally, if the applied voltage is more than the barrier potential, the diode starts conducting and a very high current flow takes place in the forward biased condition. So in that case, the diode conducts current through it. So in the reverse biased condition, there is no current flow through the diode. The forward biased condition, there is a current flow through the diode. So this property of the PN junction has utilized in circuits for certain purpose, like rectification of alternating current in order to produce DC, or you can use such device as a control device of current, that is on-off switch. You can consider it as an on-off switch. When it is forward biased, it will conduct current, that is on condition. When it is reverse biased, it will not conduct current, that is the off condition. So likewise, the device, PN junction device, that is PN junction diode, can be used as a rectification device in rectifiers to convert AC into DC, or it can be used as a control device for controlling the current, that is as a switch, either to control the current through a circuit or not having current flow through the circuit, on-off switch. Okay, so that is the conditions here I told you. Current flow in reverse biased PN junction diode due to the minority carriers is called reverse saturation current or leakage current, which is usually called reverse saturation current or leakage current. If the leakage current is increased more and more, what happens? There is a limit for the applied voltage that is more than the peak inverse voltage, at which diode PN junction will be getting damaged and a very large current will be flowing in the reverse direction. Of course, in that condition, the diode will be getting damaged. So the current which is flowing in the reverse direction during the reverse bias condition is called reverse saturation current or leakage current. It is in the range of nanoamperes or microamperes. In the case of silicon diodes, this reverse saturation current is very small, in the order of nanoamperes, very small current. In the case of germanium diodes, it will be of the order of microamperes. And this reverse saturation current or leakage current will be increasing with increasing temperature. It increases with temperature because minority carriers are thermally generated. We have already seen in the p-type and n-type semiconductor materials. The minority carriers generated in the materials are due to thermal generation. It is thermally generated carriers. So this minority carriers which are thermally generated, that will be crossing across the junction, producing a reverse saturation current or leakage current, and that leakage current will be of the order of nanoamperes in the case of silicon diode and microamperes in the case of germanium diode. So now we have learned PN junction diode, how PN junction behaves when there is no voltage applied, when there is no external voltage applied, and how PN junction behaves when a source of potential is applied in the forward direction or forward biased condition. What is a forward biased condition? What are all the necessary conditions for forward biasing? What is the barrier potential? How the barrier potential can be circumvented in order to have a current conduction through the PN junction when it is forward biased? And how the junction can be, or how this particular device can be used as a current control device, that is switch. How this device can be used as a rectification device. In reverse saturation, in reverse bias condition also we have seen the nature of voltage applied across the PN junction. Here the voltage polarity is reversed, and even then what all things happened in the junction, how the depletion region is widened, and what actually makes the current flow through the PN junction under reverse bias condition, that is reverse saturation current. What will be the nature of the reverse saturation and what is the value of reverse saturation current? For silicon is nano ampere orders. In the case of germany, it will be of the order of microampere. And how this thermally generated, how this particular reverse saturation current is taking place, or how it flows, or how it crosses across the junction, how it flows through the junction. And that is essentially minority carriers that are all thermally generated. So with this particular portions and topics, I conclude this PN junction diode and its forward biasing and reverse biasing and all. And the detailed aspects of this one will be available to you in the notes, which I will most probably today itself I will be forwarding. I will be uploading all those things with the videos, and you can go through the videos. Of course, the water video I have prepared due to the in the class here itself, that is in the Google Meet itself, that will be uploaded. That will be uploaded. That will be a bigger video sometimes. But you can see all those videos in the Moodle. I will upload all those things in the Moodle. Okay. So with this, I conclude the session here now, and wish you all a very happy and nice day today. And now I will take the attendance. Okay.